Alrighty then, welcome to the next episode of Vision Basic. This video is the next in a series of videos centered around making a multi-directional smooth scroll game. When I make videos like these, the goal isn't to create a completely finished game. My videos are intended to teach you how to program, so feel free to take this game and make it your own by adding your own personal touches to it. Another goal I have is to make shorter videos and put them out more frequently, if possible. So I do plan to focus on smaller bites of the process for you to chew on in future videos. After spending weeks on prepping for this video, I want to get it out there quickly. So I don't plan to jazz it up with a whole lot of charts and graphs or whatever. Okay, let's jump right in and see where we left off. And we're going to warp it for here for a minute. This version of my game has been somewhat modified from what you last saw, though visibly you wouldn't know it. When I created the sprites for this game, I realized that the direction of rotation was opposite of normal degrees, and that my sprite shape started with the ship at 90 degrees. So that just made some of the math in the game more complicated. Long story short, I wrote a small program to correct the order of my sprite shapes and then save them back out to disk. So now my first sprite shape faces to the right at 0 degrees, and it now rotates counterclockwise. And the game program has been modified to accommodate these changes as well. In this video, we're going to focus on adding enemy ships to the mix. But first, let me show you some changes we're going to make to the placement of the player ship on screen. If you watched my TPUG presentation, then you might have caught a glimpse of what's about to happen here. It involves the array swingcos, or swingcos, or whatever you want to call it, that never got used in my last video. Notice that the player ship is in the middle of the screen. For starters, the dynamics of movement are a little bland. As you can see here, it just sticks around there in the middle of the screen. But also, you can see that we don't get a decent view of approaching enemies from where the ship is situated. If you only get a half screen of warning space. So my idea was to swing the ship back and away from this central spot on the screen and to rotate around the central spot. Let me show you what changes are needed to make this happen as it explodes. Okay, this is our routine that moves the player ship around. We're going to add variables swx and swy to the mix. These variables will be our swing additives for our ship to help push it away from the center of the screen. But first we need to set default values for them. So let's list the area where our defaults are set. And I'm just going to create line 1040 here and type the following. And I'm going to have to type this one out, but I'm going to try to copy some of these things to speed up the process, but I don't have this line ready. So, oops, sorry. Okay. San equals plus 90. Swing x equals swing cos n, and swy equals swing cos sin. Okay, hopefully I typed that in right. Okay, enter. Now these additives place the ship about 70 pixels away from the center of the screen. If you recall from our previous video, many of our values have been multiplied by a value of 64, so that we can add more accuracy to the mix without using decimal values, since decimal values are slower to work with than integer values. The swing cost array already has been amplified by a factor of 64, and then also amplified by the additional 70 we need to move the ship out from the center by 70 pixels. We use the san variable that I typed in to allow us to cheat and use a single array to produce sine and cosine related values for us. This technique was explained in the prior video. So let's list 3000 to 3090 again and add some important lines to the mix. And for some reason I want to say mixed, and I don't know why. Okay. Keep in mind that our ship is at center stage no matter what we do, in the sense that everything is affected by the position of the ship on the screen and the position of the ship within the grid. Let's imagine that everything on the screen is stationary and that our ship is moving left. In effect, everything else will appear to be moving right. So even though everything else has its own trajectory, we have to take whatever our ship is doing and subtract that movement from everything else. This includes our lasers too. It gets even more complicated with the swing motion we're about to introduce. Let's make some changes to the code. I'm going to make this line, and this line, that line, and this line, that line. And I need to go back over. Okay. And now I'm going to paste in some modifications here. Enter that line. Now, as you can see here, the only difference here in these lines is that we've added the SWX and SWY to the end. Now we're going to need to copy the old values of SWX and SWY to create a difference that we can use to help adjust the movement of everything else besides our ship. So we'll add this line. It just came to my attention that I sat there and renumbered these lines and then went ahead and I had this planned differently. Blame it on the aging mind. Okay, now let's define the difference between the current location of our ship's swing and the previous location of the ship's swing. Say that 5 times fast. Let's imagine that the player's ship is at the bottom of the screen, facing up, and the player is steering his ship a couple degrees to the left. Remember, we're rotating the ship about the center of the screen, so the ship will appear to move left a tiny bit, and perhaps a tiny bit upward. The background image and other sprites on the screen will also have to follow suit. So we use this difference to make adjustments for everything else on screen. These two differences here, DFX and DFY. Next, let's add this line. Here we have added the swing difference to the ship's directional X and Y additives. And we need to modify this line. This makes all the necessary adjustments to the ship's location within the larger background image map. Despite these variables being added to the image map location, DFX and DFY will be subtracted from everything else, all lasers and all enemy fighter positions. And let's clean this up a little bit. List it. Okay, a little cleaner now that things aren't jumbled. Now, when I played the game with the changes, the steering just felt all wrong. It's fine when the ship is at the center of the screen, but for some reason it feels wrong when you have the ship rotating about a center point. So I chose to reverse things. So I'm going to go up here to line 3110, and instead of subtracting our joystick feed from our angle, we're going to add it. Oops, sorry. Boom, there we go. Now when we press left, the ship will appear to rotate out to the left direction, but really will be steering right. You'll understand this better when we run the program again. Now we have to make adjustments to the laser's position on the screen. Oops. No. And we're going to add a line here. This line is needed to help push the lasers out and away from the center of the screen as they are ejected from the player ship. This is because at this stage of the program, variables SX and SY in line 1040 represent the player ship's original and static coordinates on the screen before swinging the ship out and away from the center. So both the laser and the player ship both end up pushed out away from the center independently. It's redundant, but this can always be changed later. Next, we have to make adjustments to the laser's position as it moves along its trajectory. We don't want the laser to turn right if the player's ship turns right. That would just be wacky. The laser needs to maintain its straightforward trajectory. Okay, so here we have replaced lines 4100 and 4110. Okay, we just need another little change here. And we're going to change this line here. Okay. To this line. And then we're going to add a couple other lines. Now here we have changed SX and SY to TX and TY. Do note. Alright, now we're ready to run the program and see if I typed everything correctly. And we're going to warp. Okay, get ready. Notice that the player ship is now at the bottom of the screen, instead of being dead center. Now let's steer this puppy. Whoa. Now this part takes a little getting used to. So you can crash it. I like crashing into things here. And if we fire off our lasers, you'll see that their movements are tethered to the background image instead of tethered to the player ship. And I think my ship exploded again. Again, we don't want our lasers doing turns along with the ship. And I need to quit crashing. It's like when I tried crashing, it was harder. And now that I don't want to crash, it's like, you know. Okay, there we go. As you can see, hopefully see that the laser is tethered to the background now, and not, it doesn't follow the ship around. And in a further version of this program, I change the color lasers to blue for good guy and red for bad guy. I will admit that it takes a little getting used to having the steering reversed. Not really in a case when the ship is at the bottom of the screen, but rather when the ship is at the top facing down like this. This is because the ship moves left when it would otherwise move right when at the bottom of the screen, and it moves right when it would otherwise move left. If using the joystick, you're not really moving left and right. Instead, you're steering left and right. And that's a rotational movement. And I can't pay attention to the screen and dish out this text. Sorry, people. You're just going to have to watch my ship do crazy things. I have a different steering system I'd like to try out for my next follow-up video in this series. Now, I want to point out that we don't have much time left in our 1/60th of a second to control an enemy ship. Where am I at? That red zone in the border on either side is not too far from the bottom border. This red zone here. The bottom border that flickers green and white here. In my last video, I explained what the color bars meant, and I explained that our goal was to try to keep all the game action confined to 1/60th of a second. This is in relation to NTSC systems, and we don't need to worry about PAL systems, because if it works in NTSC, it's going to work in PAL mode. The PAL version of this game is going to run visibly slower. This could make changes to the math. Yeah, I'm sorry, I'm reading wrong. You could make changes to the math in this game to make everything appear to move the same speed on both systems. You just need to multiply all of the distances moved by each sprite by a factor of 1.2 if making a PAL version of this game. Okay, and I'm just flying aimlessly here. I can't multitask, people. I gotta either say the text or play the game. Now, I think you can multiply by a factor of 1.2 by multiplying the integers in this game by a factor of 77 instead of the 64 that we've been doing, and then still divide by 64 at the appropriate time. Again, see the first video of this series for a better explanation on why we are multiplying many of the values by 64. And I'm going to pause the border here. Okay, pausing things here. The white at the bottom and the green border at the top represent the portion of the program that moves our sprites while the raster beam is not drawing the main screen. Actually, the zone is all green, but I cannot show green up top and green at the bottom at the same time. We don't want our sprite shapes to flicker or shear, so the best time to move them is when the raster beam is off screen. I created a user-defined command to move the shapes, but there's a lot of overhead involved in transferring the parameters of the user-defined command over to the receiving variables on the other side. This user-defined command is necessary because all of our sprite coordinates are inflated by a factor of 64. So we have to strip off the excess bits of each coordinate before plugging the proper values into the mob xy command. This overhead highlights a downside to employing user-defined commands when speed is of the utmost importance. So I'm going to show you an alternative technique that speeds up that overhead significantly. Granted, everything I'm about to show you is going to be replaced by something even better, but this is a teaching moment and is applicable to many situations. First, notice the combined size of the green and white areas at the top and bottom of the screen, here to here. And next, notice where the red area in the border rests, and notice the distance between the red area and the white area at bottom. So just kind of pay attention to the thickness of this, and how far this red area is from the bottom. And also pay attention to the blue too. But basically the red part is mid-screen. Okay, pay attention to all that. Got it in your mind? Good. Okay, now we're going to exit. Oops, okay. We were going to exit. There you go. Lines 11, well, how do I say that? Lines 11,020 to 11,050 handle dividing the x and y coordinates by 64 by repeatedly dividing the variables by 2 6 times each. Right here. The half command is super fast compared to simply dividing each variable by 64 in a math expression. Okay, so we're going to eliminate the recipient variables in line 11,000 and remove the local command. So we're going to type this. I could just go up there, but we'll just type it. Okay, maybe I should have just edited it. Okay. And we're going to remove the global command too. So in this line here, remove global, and up here we've basically whittled things down to just the procedure sprite called sprite. We're eliminating all this stuff here. And then we're going to change how we call our sprite routine. Alright, now pay attention to this line here. We're going to replace this with something different. Okay, there you go. And press enter. Instead of calling the sprite routine as a user-defined command with trailing parameters, we are transferring our parameters directly into the recipient variables at machine language speed in these lines here. And then we're calling the sprite routine at machine language speed as well. We need to take care of the laser too, though. Notice in line, this is the laser line. Okay. And let's list things again. I actually use this technique in my Herald game if you examine the code. It's certainly not as elegant to go this route. I think I normally say route, but it does execute a lot faster. And generally, you should be able to read what the code does when looking at it, the lines that I've added. Again, it's just not as elegant. So let's see the difference. Shall we? By running the program. And warp it. And load the files. I guess we don't need to load them every time. You should notice that the red zone on either side is significantly higher now, and thus giving us more time to perform game functions. Keep in mind that we are only handling 3 shapes at most right now. So what you saw earlier would have been significantly worse if we had all 8 sprites being plotted. So notice up here that the green area is now gone, and the blue has been shoved up all the way up, and our red is no longer mid-screen. Okay, next I'm going to show you various stages of game development. Let's load our next file. Run it. And I guess we'll load the files. Here I was working on having the enemy fighter, the red one, try to hone in on the player ship. Even though you see the player ship at the bottom, the enemy is focusing on the player's origin point, which is still at the center of the screen. It appears sluggish because we're printing some data at the top of the screen. We can speed it up by putting things in warp mode if you'd like. But notice the smoothness of the movement. I'm just reusing the fighter shapes for the enemy because they look kind of cool this way to me. The red color looks sinister. As you can see, the enemy ship is perfectly able to orient itself towards the center of the screen. This actually is no easy task because it's trying to hone in on a coordinate that can be moved about, and the math behind it is fairly tricky. Moving a bad guy towards a specific point in the straightest way possible isn't exactly that difficult, but rather figuring out I'm jumbling my words, figuring out the angle related to that trajectory is the difficult part. You have to know the tangent value of that trajectory and then convert that tangent into an angle value. Regular Basic provides the ATN function, arctangent, that could help you with that. But it's a very slow function. Vision Basic doesn't natively support that function anyhow, and again, it's a rather slow function. You really don't want to use it in your game. A common technique used in games is to have your enemies move left, right, up, down, and perfectly diagonal at 45-degree increments. This keeps things simple, but it also produces unnatural movement. Many games don't have room to provide sprite shapes for each 10 degrees of angle facing. As it is here, you can see that I'm reusing the ship shape. So anyway, just to illustrate what I'm talking about, your normal movement, just follow my arrow, would be like, okay, let's just say the ship is here and the enemy is like somewhere over here. What it'll do, typically what you would normally do in your like simplified math, is just kind of, you would follow, the enemy would follow towards your ship, going about 45 degrees, and then immediately just immediately go in a straight line. So it would go doom, doom. Okay, and that's kind of what I'm trying to explain here. Okay, so what did I do here? What was my solution? I decided to divide the spectrum of facings of the enemy into 4 quadrants, and then I divided each quadrant into 2 parts. Then I used the tangent value between the enemy ship and the player ship and compared it against a set of values narrowed down to 45 degrees. Because each quadrant being divided into two parts results in a 45-degree range. I chose this technique because it seemed better than focusing on the entire 360 degrees and the entire range of tangent values within that range of angles. This topic would be too lengthy to describe adequately in this video, so I'm just giving you a bare bones explanation. In the upper left-hand corner, you can see that the first value is the quadrant the enemy is facing, numbered 0 to 3, and running in counterclockwise fashion. The next value is either 0 or 1 and represents a half of the current quadrant. A value of 1 is for more vertical facings, and a value of 0 is for more horizontal facings. So a value of 1 would be, if the enemy heading is kind of like up here and down here, and a value of 0 would be for facings in these horizontal directions. And then the third value is the perceived angle that the enemy ship is facing. We can see that the program is figuring out this angle quite well by using the quadrant, the half quadrant, and then the tangent to figure out which way to orient the ship. I will say that there was a lot of trial and error behind the scenes, so this ship in earlier drafts of the code wasn't always facing correctly. Okay, let's keep rolling. Warp it again. Yay. Okay. Once we get it visible. Okay. This stage shows that the enemy can locate the player ship, but there is no detection for when the enemy goes out of bounds. So their coordinates exceed those of the screen size, and that's why the enemy ship tries to go straight up at times, because its coordinates extend well past the bottom of the screen, and you're just seeing a wraparound effect. The yellow zone in the border represents the part of the program controlling the enemy ship. This section of code is actually quite fast, but keep in mind that we are only controlling one ship, and we haven't even added any enemy lasers to the mix yet. So that red zone is getting dangerously close to the bottom. Not good. And notice that by adding another sprite to the mix, that little green sliver at the top is inching its way downward a little more. Before, we had the blue shoved all the way up to the top. So now we're starting to see a little more green again. So anyways, I'm going to have a little fun here. But you can kind of see that the enemy ship is trying to hone in on me. Now this game is kind of like the way I have it set up is kind of like a kamikaze type thing. I mean, like, these enemy ships are, their goal is to pretty much either shoot me or crash into me. So they are not concerned about their own well-being. Okay. And I can shoot, but it won't. I don't think it'll do anything to the ship. Yeah. Okay. Anyhow, hope you're enjoying this so far. And on to the next stage. Just kind of showing you my progress as I kept going forward. Maybe it's interesting, maybe it's not. Oops. Let's replace it. Okay, and run. And warp it, sorry. And push yes again. Alright, this stage has the ship spawning at a new location when it goes out of bounds. I have the ship spawn at the opposite facing of the player ship. The reason for this is that if you have it spawn to either side or from behind, it likely won't be able to interact much with the player ship. Plus, you wouldn't want the player to get quickly attacked from behind. Okay, let's go ahead and move it around. But as you can see, the enemy is spawning. Love that word, spawning. Do you spawn? I don't know. That sounds kind of personal. Yes, I spawn every Friday. Okay. I don't know how you might take that. But anyways, let me see. I'm gonna fire some lasers. I don't know if I still don't think. Yeah, I don't think the enemy is ready to explode yet. But anyway, as you can see, the ship just keeps respawning. There's actually no delay either, so it just pretty much immediately spawns. But you can see it's homing in, honing in. I don't know if honestly, I don't know if I'm using the right word. Home, whatever. I think you're supposed to hone your skills and home in on something. It's alright, people. It's alright. Okay, let's go on to the next stage. I have many stages here. That's why it took weeks to get to this point. Okay, speed up that compile. Okay, realizing that we were running dangerously low on computer cycles, I decided to create a better routine to handle plotting of the sprites to the screen. The routine I created employs assembly language and it handles all 8 sprites. The mobxy command is pretty fast, but again, with higher level languages, even compiled ones, there is a certain amount of overhead you just can't avoid. Now, some might criticize my use of assembly language here, but keep in mind that Vision Basic allows the mixing of both basic and assembly language. So why the heck not? Let's use some assembly language, dang it. Besides, even if you're a basic programmer, you can copy the code of this routine and use it in your own programs without even knowing how it fully works. You just have to plug some variables into the code and voila. Anyhow, notice how we've shoved that blue zone in the border back up top. As a matter of fact, you can see that all 8 sprites get handled in the thin green area at the bottom. As you can see, well actually you probably can't see this, some of the blue even creeps up through the bottom. I'm just not recording it, that little section there. Well, you might, yeah, you won't be able to see it in this video, but it's there. Just somewhere around the bottom here is like a little thin area of blue. Anyhow, we'll move the ship around again because I just love steering my ship. Oh yeah, now we got blue lasers. Forgot. Yeah. And I still don't think we have explosions yet. Bam. Okay, enough playing games. Let's look at this super fast sprite routine, shall we? All you need to do to use this routine is to plug in all of your x coordinates in this row here, all of your y coordinates in this row here, and all of your shape values in this row here. This routine handles it all. The code you see here might look foreign like heck, but you don't need to know a lick of it. Just plug your values right in. Okay, let's move onward, shall we? Alright, get ready for it, folks. So here is where I added 3 enemy ships to the mix. Unless you get into the complexities of multiplexing, you need to figure out your limits. I could add 1 enemy laser and 1 more enemy, or I could add 2 enemy lasers and stick with the 3 enemies. But I think I'm going to just have 1 enemy laser and at a future point give the player 2 laser sprites. So our tally here is 2 sprites for the player ship, 2 sprites for his lasers eventually, 1 sprite for the enemy lasers, and 3 sprites for the enemy ships. That's 8 sprites total. But notice that the yellow area in the border isn't a whole lot bigger, and yet we are controlling 3 ships on the screen somehow. How is this possible, you might ask? Well, I'm employing a trick I've mentioned before, and I use this technique in my Herald game. See, if you don't always have to give decision time to each sprite for every screen refresh. In this example, each enemy takes a turn, being the focal point during a single screen refresh. For 1 screen refresh, it's the red ship. For the next, it's the yellow ship, and finally, it's the purple ship. Now, you still need to move all of your sprites if they are appearing on screen, but they can all move along predetermined trajectories when it's not their turn to make an intelligent decision. Simply advancing a sprite on screen can be a very fast procedure. So employing this cheat of sorts can make a lot of sense. This technique can be applied to any language, even regular BASIC. In the case of the enemy ships here, when it's time for a ship to make a decision, it can compare its trajectory against the trajectory it should be on, and simply change its heading a little. As you can see, all 3 ships are aiming quite well towards the player ship. And I still don't have them able to explode yet. I'm sorry. Don't worry. It's like swatting gnats or something like that. It's like, get away from me. I'm trying to eat dinner here. But anyways. Okay. But these ships aren't shooting any lasers yet. Well, let's see if we can do something about that. Okay, by this point I have the enemies, well, we gotta wait for it. By this point I have the enemies shooting lasers at the player, and now we can shoot at the enemies and blow them up, which I'll demonstrate. You have to figure out which ship should do the shooting because you only have a single laser sprite to share between all of them. So I chose to focus on the ship that's closest to the player. Now, the proper way to calculate distances is to take the square root of the combined x distance squared plus the y distance squared. And what I mean by x and y distances are the differences between the x and y coordinates of an enemy ship and the player ship. But again, we can't be using slow functions like square roots in our game program. We just can't. So we can use a somewhat less accurate method of simply adding the x and y distances together to get a total, and then compare the distance totals between all 3 ships and the player ship. And then we should also take into consideration whether or not an enemy is pointing directly enough at the player. I mean, why fire a laser if you're not even pointing fully at your target? With simple math and fast comparisons, this can all be done rather quickly. Okay, they are just coming at me. It's like having those gnats shooting stuff at you. Now, keep in mind, people, this is you can't do this kind of stuff in regular basic, but the point of Vision Basic is to prove that you can do this kind of stuff a lot more easily. I mean, granted, this game is the programming here is complicated just because we're talking about tangents and stuff, but the point I'm trying to make here is this game is not completely written in machine language. Okay, let's exit. Now we're going to load game 18. Now these things are numbered. You know, I would save them, you know, change the number each time I saved it. Sometimes I would copy over, you know, an existing version, but every once in a while I would increment the version number. Alright, we're ready for the game as I have it right now. I can shoot them when they're visible. They can shoot me, and they can ram into me too. I've decided to slow the enemies down a bit and make their targeting less accurate, and I also added a delay between their firings. I think I also increased the speed of the player ship. I had to make these changes because they were simply killing me too easily. They were simply too good. Now, as the level increases, we can improve their skills, and we can even just start off with just one enemy and gradually increase their numbers. We can even employ a system of shield damage so that they can't destroy me with just a single laser blast. Anyhow, I need to defend myself here. And I'll just, look, I'm going to admit, and I think I've admitted this before, but I'm not a very good game player. So, I think this would be probably a little easier with a joystick, though. I'm having to use my keypad. Let's at least shoot somebody. Come on now, come on. No. Or ram into them or something. Come on now. I gotta show off the explosions, man. There you go. Oh. Okay. That was kind of cool. Okay. Oops. Okay. Let's exit. So let's look under the hood and discuss some of the new stuff I've added. I need to make it clear that all of the editing I did earlier in this video was to an older version of the program, so the code you're about to see isn't going to be identical, and I'm not going to go over all the smaller changes between the two. We're mostly going to be focused on the enemy ships and the programming behind them. So from here on out, this is more about programming, not so much demonstration. So, you know, if you just like the visuals and stuff like that, okay, we're done. I'm going to go into the programming part now. So for those who are more interested in looking under the hood of this vehicle, well, let's get started. Here I just want to point out that I have an array here for the lasers, laser costs, whatever, in this line here. And I haven't actually used it yet. I'm pretty much using the speed of the ships to determine the laser speed for now. I'm leaving the array in the program for now in case I change my mind, but it is costing about 900 bytes of RAM to have this array, so if I end up not needing the array, I can delete some lines here, and it will also speed up the game startup, as the data doesn't have to be loaded into the array. I think as it is, it takes like about 4 seconds here. Actually, I put on, yeah, see right here, clock, 4.3 seconds, and I don't even know if that's a current reading, but in order to run this whole section here, it takes about, according to my last estimate, 4.3 seconds. So if we eliminate the laser cosine thingy, it'll probably shave off, I would think, at least a second or so. Anyhow, let's go on. Here I've added sprite definitions for all of the sprites in the game. Again, sprites 0 and 1 are for the player ship. Sprites 2 and 3 are for the player lasers, though we're only using one of them for now. Sprite 4 is for the enemy lasers, and sprites 5, 6, and 7 are for the enemy fighters. Here is where many of the variables for the game get initialized. I probably need to add more variables here, but I am a little bit messy with my programming. Problems and glitches could arise if some variables aren't initialized here. In line 1002, I've renamed variables SX and SY that were there to CX and CY, since they more accurately represent the center point of the screen that the ship rotates around. So I'm just using C for center. In lines 1040 to 1044, I am defining the enemy X and Y coordinates and the angle that each enemy is facing. E1X is for the first enemy's X coordinate, E1Y is for its Y coordinate, and E1A is for its facing angle. In line 1046, we have target angles for each enemy ship. You don't want to simply have each enemy instantly pointing at the player's ship the whole time. That would be unrealistic. So we figure out a target angle and then have each ship gradually steer towards that target angle. And to note, the target angle is always in flux because the player's ship and the enemy ships are always moving. In line 1048, we have a counter of sorts related to whether or not each enemy is live. Non-zero values mean that the enemy is either exploding or being timed for re-entry into the playing field. Each enemy ship gets its own unique variables. We could use arrays to simplify things, but as mentioned in the previous video, if you want serious speed, you're going to have to limit how many arrays you use. Again, it's all about the overhead. In line 1050, we have X and Y coordinates for the enemy laser that they all share. We also have an enemy version of the variable leçon. I just tacked an E in front of it. It indicates if the laser is on screen or not. Line 1052 has the variable ACCU to set the aiming accuracy for the enemies. The larger the value, the wider the angle of inaccuracy, though oddly enough the enemies still end up with pretty decent aim. I think a higher value tends to cause the enemy ships to start shooting from further away, actually. Next to that variable is a timer for the enemy laser. Originally, the enemy firing would become more frequent the closer it would get to the player. You might have noticed that. So this variable helps to establish a delay. In line 1060, we have the turn tightness factors for both the player and the enemy ships. If you increase the speed of a ship, you should also increase these values. Larger values allow for tighter turns. The values here are angle-based, so the 3 represents a 3-degree. So the 3 represents 3-degree increments, and the 1 represents 1-degree increments. In line 1070, we have the current enemy ship that gets to respond intelligently to the current screen refresh. Remember, each ship takes turns deciding the direction it is going to go. So this variable advances with each screen refresh, well, except for the refresh dedicated to drawing the background. It will cycle forward from 1 to 3 and then start back at 1. Next comes the curlim variable, which actually limits the number of visible ships on the screen, so the current variable will only cycle up to the value contained by the variable curlim. There are some changes here. I've turned some of the assembly language into routines that you can copy into your own programs without having to understand how they work. The first is the check routine, CHEQ, in line 1105, which checks for the Q key being pressed. If the Q key is being pressed, the program will exit. And next is the catch routine, which is called in line 1110. This routine appeared in the recent ball bounce video that I did. It waits for a specific raster line before returning control back to the program. In line 1170, we call two routines that control the enemies and their laser fire. And the call to line 5700 is for checking to see if the player has been struck by an enemy ship or laser. I just haven't given the routine a name yet. In lines 1180 to 1190, we are cycling through which enemy ship gets to make some intelligent decisions. Here, the routine at 2000 checks to see if any of the enemy ships have been hit by the player laser. The distance between the laser and each ship is measured, and then a routine is called to check for collision. We're not using the sprite-on-sprite collision register for any collision detections in this program because the collision register is seldom useful at helping to sort out which two sprites are colliding. Instead, the collide routine, collide with a question mark here, right here, gets called, and if the enemy in question has been hit, the then flag, THN, you know, when you use the then command or statement or whatever, there's a flag associated with it. The then flag will be set. So, for example, if the then statement is executed in line 2030, we will set the enemy life flag, EL1, to a value of 1 to start the explosion process. There aren't any significant changes to the player ship control routine here, and I showed this off on my last video, the last video about this game, except that now we are using SX and SY instead of TX and TY in line 3050. And remember earlier that we had changed SX and SY to CX and CY. SX and SY didn't make sense to represent merely the center of the screen, so that's why they were renamed to CX and CY, and TX and TY were meant to be temporary, but instead get used a bit, so they were renamed to SX and SY because they better represent the player ship coordinates. It's a little confusing, but just follow the logic. Think S for ship and C for screen center. Okay, here is the routine that handles enemy firing. First, in line 5002, if the laser is on, we can skip forward to line 5500 to check and see if it is out of bounds. Next, in line 5004, if the player is exploding, there is no need to fire at the player. In line 5006, we have that delay timer for the enemy laser. If not in progress, then skip to line 5010 so we can proceed with a possible laser launch. Otherwise, advance the timer with an increase. I'm having to skip through this pretty quick, people. It's just, this video is going to be longer than I want anyway, so hey. In line 5007, if the timer is less than 40, we're going to exit. Otherwise, we're going to clear the timer in line 5008. The next several lines get distances between all of the enemy ships and the player ship. If a distance is 32768 or greater, that implies that it is negative. So we force all quote-unquote negative values into the positive by subtracting them from 0. Again, we're using integers, keep that in mind. There are no negatives here. We combine each x and y distance together and then feed them into variables dis1, dis2, dis3, that sounds funny, as seen in lines 5030, 5060, and 5090. I mentioned earlier that these distances aren't true distances, but they will be close enough to the real deal to get the job done. In lines 5100 to 5120, we compare all three distances to see which enemy fighter is closest to the player ship, and then branch out to three different sections of code based on those comparisons. Lines 5200 to 5280, for example, are executed if the first enemy ship is the closest. Line 5200 checks to see if the first enemy is even alive, otherwise we'll move on to the next enemy ship. Lines 5210 and 5220 compare the enemy's target angle against its current angle to see if it falls within the accuracy zone we set up through the value we placed in the variable ACCU. If it doesn't, we'll branch to the code involving ship number 2. And my voice is getting raspy. I'm sorry about that, people. If all is well and good, we'll turn the enemy laser on, we'll define the shape for the laser, we'll set up the X and Y additives for the laser, note variables ELXP and ELYP, and we'll set up the starting coordinate for the laser in variables ELX and ELY. I wish I could explain the details better here, but I'm trying to keep the length of this video down. Notice that in all of the code you see here that I'm using fast math and comparisons for everything. This is how we keep things super speedy, because everything here gets converted into pure machine language. You can always start out with regular math expressions and if-then statements and then manually convert everything once you know that it all works the way that you want it to. Convert it into the faster commands. Okay. Notice that I've pretty much copied the code for enemy 1 and used it for enemies 2 and 3 here, making some changes here and there, of course. And okay. And starting at line 5500, we are moving the laser until it gets out of bounds, as long as E leçon is non-zero. That pretty much sums up all the lines of code you see here. Notice in line 5510, we are adding the laser X and Y additives to the laser's X and Y coordinates, and in line 5520, we are adjusting the X and Y coordinates of the laser with respect to the player movements. The comparison values in lines 5530 to 5560 are all inflated by a factor of 64, so the comments on each line indicate the real screen coordinates we are comparing against. Line 5600 starts our routine that turns the laser off. This routine is called when the laser goes off screen or if it hits the player. Here we force the X coordinate way off screen and we start the timer that delays further deployment of the laser until the timer is up. This routine here checks to see if either the enemy has collided with the player or if the enemy laser has collided with the player. In lines 5700 and 5705, if the player is entering new life mode, where the ship flashes, or if the ship is exploding, we simply exit the routine. The rest of the lines in this routine get distances between the enemies and the player and the enemy laser and the player, and call the collision routine starting at 5900. If the player has been hit, we increase the explode variable. If the enemy has hit the player, we increase the enemy life variable for the appropriate enemy, either EL1, EL2, or EL3. These variables then become timers, which help to dictate which shapes are being used for the explosions. These timers also delay the introduction of a new ship until the timer has finished. Something you might have noticed is that when a ship explodes, it keeps moving along its final trajectory. It's things like this that you need to keep in mind when programming. You don't always think about these things until you see the results of your programming, and then you think, gee, that doesn't look quite right. Then you start to make changes to your code and realize just how complicated your programming can become. I've learned that timers are a great tool to time all kinds of events in a game, so use them, people. Okay, and line 5900 starts the routine that checks for collisions between two sprites. Any two. Before entering the routine, you simply have to supply the x and y distances in variables disx and disy. We make both values positive if necessary in lines 5920 and 5940. This routine checks to see if two sprites are within 14 pixels of each other both vertically and horizontally. Again, our values are inflated by 64, so a value of 14 becomes 896. To come up with a value of 14, I was in the Spreadator program. I placed a ship sprite next to a laser sprite at a distance of exactly 24 pixels, since a sprite is 24 pixels wide. Both the ship and the laser were pointing straight up. Next, I inched the laser closer and closer to the ship until it finally overlapped the ship on the closest side by just like 1 pixel. Like they're just like touching. Just boom. 10 pixels later, we have overlap. And that 10, you subtract the 10 from the 24, and therefore you get the 14. I figured that this was a good enough value. Granted, it's not perfect, but it seems to work. The ships could possibly touch by a tiny bit and not issue a collision, but I'm good with that too. I just want to keep the routine simple. This is where the enemies get controlled. Lines 6010 to 6030 just set up some tags or labels to poke color data directly instead of using a color command. This saves us from having to use two commands to set up the color, but the speed difference isn't really that huge. The lines from 6100 to 6290 control the first enemy. In line 6100, we are copying specific variables for enemy 1 into generic versions so that we can call routines that are common for all enemies. For example, the go sub in line 6110 calls the routine that checks to see if the enemy is out of bounds. Variables returned from the routine will be copied back into the enemy 1's variables. Again, this swapping of variables is done to avoid using array variables, which are considerably slower because they have too much overhead, and I've said that a few times already. In line 6120, if the enemy is alive, the EL1 variable will be 0, and therefore a branch will occur to line 6200. In line 6130, if variable EL1 is greater than or equal to 38, we're going to skip a couple lines. See, when EL1 ranges from 1 to 37, the enemy ship is exploding. So line 6140 sets the explosion shapes and colors, and line 6150 advances EL1 by 1. We branch to line 6230 here so that the exploding ship can maintain its trajectory. Just go pretty much straight. This routine is a little messy and complicated, but that's how it be, you know. Line 6160 checks to see if the dead enemy cycle has reached 120. See, when EL1 ranges from 38 to 119, the enemy is delayed from reappearing and he is kept dormant. So if the enemy is dormant, we branch to line 6300 where we focus on enemy 2. But if the end of dormancy has been reached, we call the spawn routine and reset the ship's color back to red, in this case, which is held by the variable C5. Next, in line 6180, we feed the generic enemy variables back into enemy 1's set of variables for x and y and angle, and we reset the EL1 variable back to 0 so that the enemy can be alive again. Okay. In line 6200, we check to see if enemy 1 is the focal point for the current screen refresh, and if not, we skip the next line. The next line, 6210, calls the routine that intelligently calculates an updated bearing for our ship, thus the name enemy bearing. Again, since this particular routine takes up a lot of computing cycles, we only calculate the bearing for one ship per screen refresh. After returning from the routine, variable TA1 is set to the target angle that gets returned from the routine. The next line, as oddly as it seems, copies the target angle for enemy 1 back into variable ETA. We could have line 6210 skip past this, but I'd have to put it on a separate line, maybe later. Regardless, to steer the enemy towards its target angle, we need to copy TA1 into ETA. Then the enemy steering routine gets called. This routine is actually somewhat simple. It just inches the enemy's current angle towards its target angle. In line 6240, we copy the updated angle in variable EA to the ship's own angle, E1A, and proceed to see if the enemy is the current one of focus. This is the second time we're doing this check. If so, we execute lines 6250 to 6270, which set the sprite shape for the enemy based on its rotation. And we also set the directional additives, which are variables E1dx and E1dy. Since all of these variables are extracted from arrays, we only want to do this for one ship per screen refresh. Again, the arrays are slower. Finally, lines 6280 and 6290 adjust the location of the enemy ship on screen based on its own trajectory and the offsets needed due to the player's own ship movements. I want to divert for a moment here to say that all lasers and enemy ships are not really tethered to the background image map. What I mean by this is that we are only controlling the sprites as long as they stay on screen. If any of these sprites go beyond the border, they vanish for good until respawned. You could, if you want, establish real coordinates for the enemies on the background image itself. This would be more realistic. It might take longer for an enemy to work its way towards the player ship though, so that's why I didn't go this route. Route. A lot of the logic of this program would have to be changed if you wanted to go this route yourself. I'm not comfortable with that word. I don't even like either of them. Route. I don't know. The next many lines are just duplicates for ships 2 and 3, so we're going to skip past them. Okay, this is the routine that simply steers an enemy towards its target angle. In 6810, we get a distance value from the current angle and the target angle. In line 6820, we check to see if the difference is less than 5 degrees. If it is, we exit. The reason we aren't worried about getting the angle exact is that the ship will actually fishtail back and forth. It looks weird, so we don't want that. I've seen it. It's weird. In line 6830, we check to see if the difference in angles is negative, and if so, we branch to line 6860, which flips the angle into a positive one. In line 6840, if the difference is less than 180 degrees, we jump to line 6900 to steer the enemy clockwise, I believe. In line 6850, we jump to 6910 to steer the enemy counterclockwise. We check the difference against 180 degrees because you want the enemy to steer in the direction that makes the most sense. You don't want to steer the ship the long way around. Some of you might be gasping at how much you have to think about when making a game like this. It can drive you mad, man, I tell you. It can drive you mad. Anyhow, lines 6860 to 6880 pretty much do the same as the lines above, except that they are here for when the angle difference is negative. We must move on. Alright, now to reveal the enemy's brains. Now this part has so much going on that I think it would take too much to fully explain. I did explain how I break things up into quadrants and subquadrants, where each quadrant is divided into two halves representing 45 degrees of range. So in line 7010, we set the quadrant to 3 just to initialize the value. Line 7020 acquires the horizontal and vertical distances between the player and the enemy in question. Line 7030 tries to see if the horizontal value is negative. If it is, line 7040 decreases the quadrant from 3 down to 2 and makes the x distance positive. In line 7050 tries to see if the vertical value is negative. If it is, line 7060 flips the quadrant value by subtracting it from 3, and the y distance is made positive. Line 7070 compares the x and y distances to see which is greater. If the y distance is greater, we're going to branch to line 7110, or 7110, and set the part variable to 1, indicating that we are going to focus on the verticalmost portion of the selected quadrant, the part of the quadrant that is more top or bottom. Otherwise, we set the part variable to 0, and we will be focusing on the more horizontal portion of the selected quadrant, the left or rightmost part. We want to avoid fractions when working with tangents, so in line 7105 we are dividing the x value by 64 by dividing it by 2 multiple times, but we are multiplying the y value by 4. This will turn our fraction into an integer value. The originally smaller y value, now multiplied by 4, gets divided by the deflated x value in line 7108. In lines 7120 to 7140, we reverse the process and divide x by y. The thing to understand about tangents is that they can range from 0, then start off as decimal fractions, and ultimately reach out to negative or positive infinity. At least my memory tells me that, so if I'm wrong, let me know. By focusing on a narrow 45-degree range, we get to focus on just some positive values between 0 and 1. Inflated, of course. Now, before I wrote this routine, I wrote a simple program in the regular C64 editor to create some inflated tangent values. I multiplied all the results by 256. This routine here compares the tangent value we created against the set of values we pumped out in the regular C64 editor. We want to figure out a somewhat rounded angle for our tangent. Line 7200 jumps to the middle of the routine here if our tangent value is greater than or equal to 106. We do this to reduce the number of comparisons needed. Otherwise, we can end up running through all 10 comparisons. In the end, we will have a target angle somewhere between 0 and 45 with 5-degree increments. And here, lines 7300 to 7400 factor in our quadrant and which half of our quadrant to flesh out our smaller angle to a full 360-degree range. Upon exit, variable ETA will have an angle range from 0 to 360 degrees. It's funny writing stuff like this because I work with a guy who was telling me that geometry and algebra were stupid and nobody uses them in real life, so why learn it? And I told him that one reason to teach a wide variety of things in school is that you simply don't know what you're going to like and dislike until you actually learn it. So how do you know if your calling is computer programming if you aren't taught such things like geometry, trig, and algebra? Because you're going to be using these things. I don't know about y'all, but I love math. I got all the way up to Calculus 2, and, well, I didn't pass it, but hey, I got that far at least. Okay, the routine at 7500 checks to see if an enemy ship is out of bounds. If it is, the enemy life value is set to 38, which is past the explosion state, and the Y value is seeded with an off-screen value that won't trigger this routine again. We don't want the enemy life variable EL to stay for 38 forever. I wish I could stay 38 forever, but yeah, we don't want our EL variable to stay 38, so. The spawn routine. This routine spawns new coordinates for an enemy ship based on the direction the player ship is heading. To simplify, as I'm not going to describe all these lines, if a player is facing up, the enemy will spawn at the top and face down. If the player is facing down, the enemy will spawn at the bottom and face up. If the player is facing left, the enemy will spawn to the left and be facing right. And if the player is facing right, the enemy will spawn to the right and be facing left. To keep the routine fast, we acquire random values from the SID chip at location 54299 instead of using the RND function. Alright, I hope I haven't missed anything. I think we're good. It's a lot to digest for sure. I plan to make the source code for the game as it currently stands available on my website. Just find this video on the media page and look for a link underneath. And that wraps up this episode of Vision Basic. As usual, I thank you all for watching my video. Please like and share my video, and definitely subscribe for more similar content. I need that now more than anything. And make sure to visit visionbasic.net.